It's the story of this meteorite, alh84001. I've got some video clips embedded in here that we can play that will provide you some background. This is an example. I mean, with the Viking mission, we were looking for, is there life currently on Mars, right? Because you can't have active metabolism without living organisms on Mars. This is one of the biggest pieces of work so far, looking for evidence of past life on Mars. So this came out the end of the 90s, just as we were heading back to Mars with the Pathfinder and Mars Global Surveyor missions. And just as those missions were reaching the planet, when we were kind of reestablishing our exploration program for Mars, this article came out describing evidence that could be interpreted as fossil evidence of past life on Mars. So it made quite a big splash. President Clinton made a big press conference and then turned the cameras over to the folks at NASA to describe the evidence. So we'll go through some of that whole process. Okay, so this is a paper that came out in the journal Science, one of the premier journals of research. Search for past life on Mars, possible relic biogenic activity in Martian meteorite alh84001. So I guess we won't take the time to deconstruct this abstract, but the main situation is we have a meteorite. The researchers are essentially arguing that it's a sample from Mars that has actually landed here on the Earth. And the big advantage of that is that we can do all sorts of laboratory investigations here on the Earth with our, very high-tech laboratories, much more than we can do sending, rovers and landers and orbiters to Mars. The story that the researchers built up is essentially there are 4 lines of evidence that they've pulled out of this meteorite that were suggestive of past microbial life on Mars. Okay, so I want to play this first video clip. You hopefully will recognize the narrator's voice. But the role of this first clip is to just provide you some of the background story of the rock itself. So what I want you to pay attention to is, what do we know actually about the rock? Where was it found? How is it interpreted to be a meteorite? Why do they think it's from Mars? What do we know about the life history, the life story of this rock? When it was formed, what happened to it, how it got to the Earth, and so forth. And you're going to want to hear this, so let me plug in.
We're all thinking that was bad.
The world was formally introduced to meteorite alh84001 on August 7th at 1 p.m.
What we've dealt with here is a single rock. You can see a piece of this rock in front of me. This rock came from Mars, UVR view. The total rock is about 4.5 pounds, 1.9 kilograms, and is about the size of a small potato.
To find out how a piece of Mars got here, the researchers suggest we rewind 4.5 billion years.
This rock formed very shortly after the planet Mars formed. What we think happened is that Mars formed by collection of small particles coming together, smaller rocks and planetesimals, and then internal heating caused it to melt and differentiate, forming a core mantle crust like the Earth. And then shortly after that, melting inside the planet produced a plutonic rock close to the surface, and that was what this sample came from. Close to the surface. Mars was warmer and wetter, and we have evidence from geology that there was liquid water on the surface. We think that some of this water came in through the fractures and settled inside the rock.
Dissolved in that water, say the researchers, were minerals called carbonates. They settled out to create deposits in the crack of the rock, much like the white stuff in hard water that clogs your coffee maker. If there were single-celled creatures then, they could have been caught as the carbonate formed.
And the rock continued to sit there with everything that it had in it until much later. The next age we have on it is 16 million years, which is the age when an impact came.
And what an impact. An object 6 miles across plowed into the southern hemisphere of Mars. It was a blast as powerful as a million hydrogen bombs. It was a blast big enough to blow some rocks right off the surface and out into space.
Yeah, the rock was projected out into orbit around the sun, not getting too close to the sun. It probably would have been sucked into the sun's gravity well, and we have never found it here on Earth. And it spent most of its 16 million year time out there.
The rock floated 16 million years in the cold dark between the worlds. Then it fell to the Earth in a hot streak of flame, only to strike the ice-covered continent of Antarctica. What followed was a quiet broken only by the hiss of the wind over the snow, a quiet that lasted for 13,000 years.
The ice moves down slowly. You must realize the South Pole is around 9,000 feet elevation. The ice fields where we have been collecting meteorites are 6,000 to 7,000 feet elevation. So the ice is dynamically moving from the interior of the continent out to the edge.
Slowly, over centuries, dry winds wear the ice away, leaving behind anything carried there by the flow. Meteorites stand out clearly against the snow, and researchers walk around and pick them up.
Our annual expedition run by the National Science Foundation collected the meteorite in Antarctica. It was actually Robbie Score, who used to work in the meteorite lab here, who was the one who found this.
I've always thought this rock was special. I know it probably sounds kind of hokey now, but it was classified as a diagonite, which made sense. Hokey now, I thought it was kind of a strange diagonite. And we collected it in the field, the clean room procedures. We had already collected 100 meteorites that season and proceeded to collect another 200 different meteorites for the rest of the season, and there you have it.
Diogenites are the most common meteorites, rocks that started in the vicinity of Hebe in the asteroid belt. There are a few from the Moon, and even fewer from Mars. And each year, hundreds of new space rocks come to Houston in sealed and locked boxes by ship, plane, and truck kept frozen all the way.
Sometime in mid-1985, we pulled alh84001 out of the nitrogen cabinet so that we could photograph it and weigh it and describe it. We then took a chip and sent that to the Smithsonian to make a very thin slice of it so that they could tell what the mineralogy was and classify it. It was about 9 years before somebody looked in enough detail to see that it was classified. I was really excited when Middleton came to me. He works for me in my research lab. I was really excited. I've got a surprise for you.
What tipped me off was the compositions of the minerals in the rock. Diogenites come from an asteroid where the amount of free oxygen is fairly low. Found out that a substantial amount of the iron is actually highly oxidized, and that didn't fit in with the original classification at all.
Gases trapped inside the rock matched exactly those detected by NASA's Viking probe when it landed on Mars in 1976. alh84001 was a piece of Mars. There are only 11 other known meteorites from the Red Planet, and this one is different. Part of the planet's crust, as old as Mars itself. Part of the planet's crust, as old as Mars itself.
Okay, so what then do we know about the rock? What's the first observation that was basically made of the rock?
Didn't they say it was a carbonite rock?
Let's go back and forget about all the interpretations and so forth. Colin?
It's as old as Mars.
Okay, that's more interpretation. Let's start from the beginning.
It's a meteorite.
That's even interpretation. What do we have when we're wandering around Antarctica? We see there's a rock, right?
That came from somewhere.
Came from somewhere. Why would we think that, first of all, it's a meteorite?
I guess they look at it, it's not an Earth rock.
Okay, so
Composition doesn't match up to be one of Earth's.
okay, this is not from Earth. So yeah, one thing would be to look and see, is this a rock that matches terrestrial rocks? Certainly can do that. It's a lot easier. There's a lot easier ways, though, to tell that something is a meteorite. I mean, what is characteristic? What experience separates a rock that comes screaming out from space compared to rocks on the Earth here? The screaming in from space is the clue. Okay, rocks, meteorites coming in from outer space. They're going to, at least the surface will be heated up very hot, and meteorites typically will have the creation of this fusion crust on the surface of the rock. Now the rock itself, if it's been a meteorite hanging out in space, it's going to be very cold while it's hanging out in space. And then when it comes screaming through the Earth's atmosphere, the surface gets heated up and produces this fused glassy surface on the surface of the rock. But the rock comes through the atmosphere so quickly that the bulk of the rock still stays at outer space cold temperatures. So it was pretty clear it's a meteorite. The other thing is, why do you go looking for meteorites in Antarctica?
Easiest place to find them.
Because
It's completely white.
completely white, and
Barren.
it's barren, and there are not a lot of terrestrial rocks that are going to be in the ice. Okay, so basically almost all of the rocks you're going to find in these glacial fields are going to be rocks that fell out of the sky. And generally speaking, most rocks only fall out of the sky because they're meteorites. Or somebody dropped them off planes. No, they're pretty much meteorites. Okay, so the rock was found when? This rock is alh84001. 1984. First important date. That's when it was collected. It's collected from the Allen Hills region of this study site. And what's the 001, do you think? It was the first one. It was collected during this study season in 1984 from this site. Okay. Now, so the actual observations is rock on the ice, 1984. Looks like there's a fusion crust. Now we start building up the interpretation. Why do they think it came from Mars? There's no little GPS chip in the rock that has tracked its travels.
They were comparing its composition with samples from the Viking mission. And
Samples of what?
was it oxidated iron? Exactly what it
The fact that it was oxidized forms of iron,
more than it would be found in the asteroid belt.
right, indicates not asteroid. doesn't necessarily say Mars, but Mars is one site where there is known to be some oxygen around. But what in more particular did they compare to results from the Viking mission? No, gases. When rocks form, they oftentimes encapsulate little bubbles of the atmosphere. We know the atmosphere on Mars is different fundamentally from the atmosphere on the Earth, different isotopic composition, different ratios of heavy and light elements in the atoms and the gases. And those gases that they identified from the pockets in the meteorite were exactly the same kind of gases that Viking identified on Mars. So they've got fairly good evidence that this is a meteorite from Mars, and then why is that very exciting news? Jeffrey?
Didn't they say that this had crust? Didn't they say that this had crust from Mars?
Yeah. I mean, we can get into some of those details in a minute, but why is it just generally exciting to have a meteorite from Mars?
I mean, it was 1 of 11.
Right.
It's pretty rare.
So it's very rare. We are currently not set up to send robotic missions to Mars, collect known samples of rock, and bring them back. That is something that scientists would love to do. This is nature essentially delivering our Mars rocks for us.
Yeah, I mean, we can study them a lot better here.
Can study them a lot better here. We've got instrumentation, we've got experimental setups here on the Earth that we can never miniaturize. Well, I won't say never, but at this point we have no hope of miniaturizing these analytical capabilities we have here on the Earth and sending them to Mars. Okay, so Mars rock, that's interesting in and of itself. I want to spend a little bit of time working backwards. 1984 is the most recent date in the life experiences of this rock. What happened 13,000 years ago?
What did happen? Oh, there was a huge impact.
No, that's the next step. 13,000 years ago is when they inferred that the rock landed in Antarctica. Okay. So, they picked it up in 1984. It didn't land that year, right? It's been hanging around in Antarctica, they think, for 13,000 years. Now, how would you tell that? How would you know the rock has been sitting around in the ice of Antarctica for 13,000 years?
Maybe the snow compared to where, like, the height of the snow and where it was buried.
Okay. There is this kind of transport process that the glacial flow is doing. So it's going to take a certain amount of time for the rock to be coughed up out at the bottom. But that'll only give kind of a rough estimate. What happens to rocks when they sit on the surface of the ground in general? They get eroded, they get weathered, and so forth. So, weathering is going to be more slow in this environment in Antarctica, but the rock is going to have spent much of its time buried in the ice. It's going to be coming down the hillside in the ice. It's going to be interacting, the surface layers are going to be interacting with the ice that's surrounding it. There's going to be a certain amount of chemical weathering that is taking place in that fusion crust that had formed. Okay, so the fusion crust forms when it's coming down and landing, and then it sits in the ice, and over time that fusion crust is going to weather chemically. And, if that happens at a consistent enough process, and you know how much has gone on, then you can tell how many years it's been sitting around in the ice. And then there was 16 million years ago is the impact that they think launched the rock off into space for it to hang around in space until it landed 13,000 years ago in Antarctica. Again, what how would they infer that based on things that they can look at in the rock? It's very similar to what we just talked about. There's not going to be necessarily chemical weathering that takes place out in space, but what's the rock going to be exposed to out in space? Radiation, cosmic radiation, radiation from the sun, and so forth. And so, if we know the radiation environment out in space, we can tell, well, this rock's been zapped, X number of times with cosmic rays and so forth. And so we infer that it's probably been hanging around out in space, exposed to this radiation for about 16 million years. Therefore, must have been 60 million years ago that something happened to throw it up off of the surface of Mars. This just gets back to the fact that we've talked about before in the class, that Mars and Earth have been exchanging spit for billions of years. And things get knocked off of Mars, they land on the Earth. Things get knocked off of Earth, they land on Mars. A lot of rock and so forth going back and forth. What's really exciting about this rock, though, is how old is the rock itself thought to be?
I think it's at about 4.5 billion.
Yeah, so over 4 billion years old, sitting around on Mars during Mars's early time. Evidence of the carbonates being laid down in water maybe about 3.5 billion years ago. Most of those 11 meteorites that we have from Mars are much, much younger than this. So why is it very exciting to have a meteorite from this time period, a rock from this time period of Mars, delivered to us as a meteorite later in history?
This, I guess 4 billion years ago is when Mars probably had more moist environment.
Yeah. So we've talked about early Mars being a much more habitable place, a much more water-rich place, probably warmer. If there were ever going to be life hanging around in the rocks on Mars, these are the ages of rocks that we would want to sample. So this is why the researchers were so excited about, actually getting and studying this rock. Okay, so this just recaps some of the things we kind of drew out. There's the evidence that this rock is a meteorite. In fact, it's a Martian meteorite. Crystallized very early in the history of Mars. It's got these fractures which would form little habitats where microbes could live if there were microbes on Mars. We know we've got a pretty good idea when it got kicked off the planet by that impact, how long it's spent in space, and it's landing in Antarctica. So I guess one point I want to make here is that you can start off with picking up a rock off of the ice, and by studying the properties of that rock, you can infer back more and more complex issues of the history of that rock and build up a whole, without that evidence, this would just be kind of isn't this a neat just so story? There was a rock on Mars, but we've got evidence for each piece of this story that the researchers have built up. Okay, let's skip this. So I want to play another clip now, which is actually going to go into the evidence that the researchers presented for this argument of life on Mars. Oh, come on. Would help if I had the right tool up. Okay, do you want to kill the lights there?
I've looked at a lot of different rock types, meteorites, different kinds of meteorites, and cosmic dust, and I'm just curious how they compare and how they differ. So this was a new kind of rock, and I thought it would be useful to look at.
David McKay, whose specialty had been moon rocks, teamed up with another Johnson Space Center planetary scientist, Everett Gibson.
Dave McKay and I joined forces, realizing that we had efforts that would complement what Dave was doing independently, we came together and Dave began to work on the microscope. And one evening we were looking at phases and we came across a segmented structure.
This is probably not the most convincing evidence, but this is the most photographic evidence.
Appeared to have like a head and a tail, and it was fat in the middle. And then it really began to dawn on me, could we be seeing evidence of biogenic activity in a microfossil life?
Although it would be quite out of character for a distinguished NASA scientist, we asked David McKay if he started jumping up and down at that point.
The only time that we really jumped up and down are when we saw some of the pictures that looked like possible microfossils. And some of those were just so impressive to us that we jumped up and down when we saw those. And that spurred us to look for more of those, and we're still looking.
They had a theory that somehow this Martian meteorite represented or contained fossilized life on Mars. I thought the entire group needed some help. Yes, I did. I was convinced that I could convince them that they were wrong.
Kathy Thomas Caperta works with the state-of-the-art in microscopes, a newly invented transmission electron microscope. It had 5 to 10 times the resolving power of the electron microscope McKay was using. She looked at those mineral deposits in the cracks in the rock.
Initially, what we did, we took chips from this meteorite that contained our carbonate globules. They have amber-colored centers, and they're surrounded by black, white, and black rims. As we take a look at this Martian meteorite, and in particular, the carbonate globules, and if we zoom in on those Oreo cookie rims, we find some very interesting mineral phases that coexist with each other that wouldn't normally do so. What we believe is that the little iron and oxygen grains that we call magnetite and the iron and sulfur grains are very similar to what is produced by bacteria on Earth.
We don't usually think of Earth minerals coming from living things, yet the white cliffs of Dover are carbonates from the shells of microscopic sea creatures. There are deposits of magnetic iron created by bacteria collecting iron particles inside themselves, and bacteria typically leave behind droppings of crystallized iron sulfide.
Finding this very unique iron sulfide phase was really exciting. And I thought, gosh, you know, we've really got something exciting going on here. And it was getting dark. It was about 7:30, 8 o'clock at night. But you know, there were no bands in the parking lot. There were no banners waving. I wanted to share it with everyone at that time. Of course, we couldn't.
David McKay started working into the night as the evidence began to pile up. He still didn't feel he could tell anyone what he was doing.
Well, there was one night in particular when you didn't it got to be about 9 o'clock, and I called Everett. He said that you got more excited about your pictures that you were taking, and you were over there in that building 13, and you were in big trouble.
Well, what do you think I was doing?
I'm not going to say what I was afraid you were doing.
What McKay was doing was looking for hydrocarbons in his meteorite. He called on colleagues at Stanford University and their brand new detection device.
They said, we have some interesting samples that we'd like you to run, and seeing what they might contain. And we'll tell you more about them depending on what you find out. You may find nothing. And they gave us these samples at that time with code names that were Walt Disney characters like Goofy and Mickey and Minnie. And we didn't know what they were.
Professor Zare was using a dual laser mass spectrometer, the most sensitive molecule detector on Earth.
The experiment is to take these samples, crack them open, and in less than 2 minutes pop them inside an ultra-high vacuum machine. So now that they're kept clean in this environment, we fire an infrared laser that heats up the sample like 100 million degrees a second. Of course, if this were on for a second, we'd have some type of thermonuclear event. It's only on for a millionth of a second or less. The result is that molecules in the rock, in the surface, evaporate. Now a plume of gas rises. and the molecules do not break apart.
Then the second laser, this time ultraviolet light instead of infrared, fires into the plume of gas. Molecules become electrically charged so they can be drawn into a detector. How fast the molecules travel to the detector tells what they are. And what Zair's team found were hydrocarbons, polycyclic aromatic hydrocarbons, PAHs for short. It's true PAHs can also be found in diesel exhaust, but
If you look at PAHs that come from the decay of organic matter, its fossilization, they tend to be simpler in structure like what we're finding.
and there were more of them inside the rock than outside, and that ruled out terrestrial contamination. And there were more of them near the carbonate globules, the other signs of life. So now McKay had 4 lines of evidence. The simple hydrocarbons that could be expected when bacteria die. Those hydrocarbons were found near other structures that suggested life. The unusual compounds in the carbonate that can be made by bacteria, and pictures of things that look like bacteria.
In my office, one day Jill came in, and I showed her one of the pictures, and without telling her anything about the project, I said,
She knew you were doing something important.
yeah, but I asked her, what's this look like, Jill? And she looked at it a while, and she laid it back on the table, and she said, that's bacteria. And it was one of the Mars pictures.
After 2 years of collecting data, they were ready to write up their findings. It was time to break the secrecy around the project. Secrecy necessary because people and the press pounce on anything connected with Mars.
Okay, so what are these lines of evidence then for past life and showing up in this meteorite?
Hydrocarbons over them.
Okay, so we've got these, they're called polycyclic aromatic hydrocarbons. They are essentially organic material. They're the kinds of organic materials you would find if bacteria had lived in the rock and had died and were breaking down. Now, is life the only way we can get these hydrocarbons? No. It's a safe answer the way I asked the question. Okay, so there are non-biological explanations for PAHs. I mean, the film clip mentioned diesel fuel burning, but that's kind of weird because diesel fuel itself is the result of what? Life, okay. So, but there are truly non-biological processes that can lead to these kinds of complex hydrocarbons. But the fact that we're finding them, and I'll show you a little bit more in detail what's going on with it. But clearly that's one piece that they were putting forward. What else? What's the most obvious piece of evidence that they put forward that would have the most resonance with people? Okay. These bacteria shapes. Now clearly they aren't bacteria, not living bacteria, not living for 4 billion years in the rock kind of bacteria. But what we would be talking about would be fossil remnants of prior bacteria that got translated into mineral structures in the rock. That's essentially what happens with fossilization. Whether you're looking at a fossil bone or a fossil leaf or fossil poop or whatever, which you know, all in all these cases, what we have for fossils that are showing up now in the rocks that we collect on Earth would be biological specimens that have over time been mineralized and changed into stone. So if you've got a giant sloth femur fossil at home like I do, It's not really bone material anymore. It's been converted to, it's been mineralized over time and converted into a bone-shaped rock. So we'll talk about these. A couple of other pieces of evidence were these magnetite structures. We have a lot of bacteria on the earth are running around with little magnets inside them, little magnetic minerals that the bacteria have produced. Why would a bacterium want to have a little magnetic structure inside? Well, it's certainly a way of sequestering iron, but the fact that they're magnetic are actually useful for bacteria here on the Earth.
Because of like our magnetic.
Okay, allows the bacteria to respond to our magnetic field. Now, most bacteria are not migrating from Canada down to Mexico, but a lot of bacteria migrate vertically in the sediments and in the water column that they're living in. And the magnetic field of the Earth is not actually straight horizontal. It's at different angles at different locations on the Earth. And so little magnetic crystals can allow the bacteria to know which way is up and which way is down. And they can move, up at night and down during the day, whatever, suits their biology. And then there is this very complex arrangement of chemicals. The carbonate globules, and then the magnetite, and the iron sulfide, and some other minerals that are found in very complex spatial patterns. Now, if you look at minerals just out in nature, they tend to be much more randomly distributed. Living organisms are much more responsible for laying things down in very, very discrete patterns. So we've got these 4 lines of evidence, and that's what the paper was built on. So let me just go through some of this quickly. These are what some of these polycyclic aromatic hydrocarbons look like. You clearly don't bother memorizing the formulas, but things like, you might be familiar with naphthalene as an industrial solvent, or I think anthracene is sometimes used in mothballs. These are kinds of organic compounds that you might come across. But the fact that they were there was a pretty striking situation for this meteorite. We have these hydrocarbons all over the Earth, though. So how do we know that the hydrocarbons that they were finding isn't just a contamination of having the meteorite sit around in the ice field for 13,000 years?
They said they found like this sort of stuff like deeper into the rock.
Yep. So that's it exactly. If we take a look here, we actually find very low levels of these hydrocarbons in the surface layers of the rock, which is what you would expect with a meteorite coming down through the atmosphere and having the surface heated up in the formation of that fusion crust. If this were terrestrial contamination, we would expect the highest concentrations of the contamination on the outside and lower concentrations on the inside. The fact that we see these higher concentrations of these PAFs on the inside really indicate that these came with the meteorite from its source on Mars. Again, the carbonate globules, again, they're evidence that they're not terrestrial. The isotopes of carbon and oxygen in the carbonate globules indicate that the carbonates formed in the rock on Mars. The shocked faulted characteristic here just indicates that those carbonates were already in the rock when the impact hit Mars and blew the rock off of Mars, because that would have been a big shock wave that went through the rock as it was being thrown up off of the surface of Mars. And then we have this very, very distinct zonation of materials that is very difficult to lay down non-biologically, but it's the kind of thing that biological organisms do all the time. Magnetite, of the pieces of information, of the pieces of evidence that were originally put forward, this is the area that probably has still the greatest amount of work being done on it. As I said, terrestrial bacteria have these little magnetic crystals in them. They use for navigation because we have a global magnetic field here on the Earth. Why would Mars bacteria have little magnetic structures inside them? What do we know about the global magnetic field on Mars? Yeah, there's not one now, but there used to be one. And there used to be one at the same time when this rock was being laid down. Okay? So magnetite crystals can be formed by physical, chemical processes, but biological formation of magnetite tends to form crystals that are much more uniform in size, shape, and so forth. And so that was indicative of potential biogenic or life activity as well. And then these fossil structures. The big problem with these fossil structures is that they're way smaller than any bacteria that we know living freely on the Earth today. So there's a lot of debate and argument about these fossils and the claim that these structures were indeed fossils. People were arguing that these bacteria would be so small, it would be difficult to fit DNA and ribosomes and the kinds of things that we know are inside cells here on the Earth inside these structures because they are so small. They could instead just be artifacts of how the rock was processed. You're slicing sections of the rock, you're doing other things to the rock. The rock's been shocked by the impact and so forth. So there's a lot of debate about the fossils here. Okay. I guess I just want to point you to these are the final two paragraphs of the paper, if I remember correctly. Here, final paragraph. Oops, pencil. None of these observations in itself is conclusive. There are alternate explanations for each of these 4 lines of evidence. Okay. The structures may or may not be fossils. The magnetite may or may not be biologically derived. The PAFs may or may not be biologically derived. But they're arguing that taken together, all 4 lines were enough to convince them that they should publish this research and make the claim that they have evidence for fossil life. We'll get back to that in a minute. I want to play this last clip, and so we just have a little bit of time to talk about the response to all of this. Go ahead and kill the light.
On the Friday before Easter, McKay and a Johnson Space Center team that had grown to 8 sent off their report to the prestigious journal Science. After a 3-month-long review, it was accepted for publication.
we sent the abstract of it up to NASA headquarters. My division chief sent it up there to the head of the science group, and they circulated it there.
As is the custom for a science paper, anonymous scientists went over the work and made their suggestions.
I remember that paper being brought up to me. He says, "Hey, Wes, look what they're going to submit." I said, "Oh boy, let's wait and see what the peer review process is." How long did that take before you got confirmation that they were going to publish it?
Well, went through 4 or 5 reviews, and then the editors had a large number of recommendations. So it went back and forth 3 or 4 times.
I have to confess, I said, this thing's not going to survive peer review.
Yeah.
The conclusions are too extraordinary.
Yeah.
So when they came back to me about July and told me, my jaw just about dropped down to here.
Really? Yeah.
And I took it up to the boss, Golden.
Wes Huntress, who's the head of space science at NASA, walked into my office and said, "Dan, I got to tell you something." He said,
This is NASA administrator like 2 years ago. Not a scientist, not a mission specialist, kind of a pompous ass, but listen to his comments anyway.
2 of our researchers at NASA Houston just had a paper peer-reviewed and accepted by Science magazine, one of the most preeminent journals in the scientific field. And he said, "You know what the subject was? They think they may have found fossilized life from Mars." It was one of those moments in a lifetime, in a millennia, where you say, what a privilege to be part of this.
After a night of soul-searching, Golden called the White House and asked for a meeting with Leon Panetta, the Chief of Staff. At 8:30 in the morning, he found himself in the Oval Office, briefing President Clinton on the meteorite from Mars. NASA kept the secret from the public for 3 weeks while they prepared a news conference for the scientists. The administrator at NASA says he was on cloud 9.
Then the rational part of my mind clicked in once again and said, I know Science magazine has peer-reviewed this, but I am in charge of NASA. The buck stops with me. So I felt I had an obligation to call in the scientists and to sit them down in front of my desk and to quiz them, to make sure that they had the proper scientific process.
We went out to Washington, they came back, and then I turned around and said, "What's this about?"
When they called from the White House. Remember that day they called from the White House?
Yeah. And I answered the phone, I was asleep.
This is the White House calling.
In early August, news of the discovery started to leak out, and NASA moved its planned news conference up a week. The press turned out en masse. The announcement created a sensation all over the world.
Rather than holding this back in the innards of NASA, we need to share this with the American people. We need to share it with the world scientific community.
Millions d'années, suivi d'un atterrissage assurément brutal, il y a 13 000 ans dans l'Antarctique. Puis c'est la mise en sommeil jusqu'à sa découverte en 1984. Alors si certains ne voient dans cette météorite qu'un vulgaire caillou.
Amerika, insansız bir uzay aracını Kasım ayında Mars'a göndermeyi planlıyor.
Amerikan Havacılık ve Uzay Dairesi NASA tarihi açıklamayı dün yaptı. İnsanlık tarihinin dönüm noktası olabilecek bu açıklamaya göre
scientists have decided we may not be alone. They think life evolved in Mars and that it's possible, even possible or probable, that life on Earth may have begun as a result of cross-contamination from Mars.
And I guess they're still experimenting with that Mars rock that they found the bacteria on. In fact, today they rehydrated it in hopes of replicating the bacteria. Actually, surprising results. Can we show that NASA footage? There's the actual NASA footage. Now you can see there's a NASA watering can. Turns out, this kind of surprised me. Look, folks, it's actually just a, well, here, look, it's a chia pet. It's a chia pet. What are they doing this?
The producers of the alien invasion movie Independence Day were quick to change their ads.
Recently, scientists discovered evidence of life on another planet. Oh my God! Duh.
So did AT&T's technological spin-off.
Just discovered life on Mars. Got work to do. Lucent technology.
The bookies in London lowered the odds of life elsewhere in the universe from 500 to 1 to 25 to 1.
This has been something, along with the Loch Ness Monster and Elvis still being alive, that we've been asked to quote odds for. So we cut the odds, basically to lower our liabilities, always mindful of the fact that early in the 1960s, we were foolhardy enough to offer 1,000 to 1 about man setting foot on the moon before the end of the decade.
And the political cartoonists had a field day.
Well, I like that cartoon from the Baltimore Sun. It shows a mild-mannered scientist giving the press conference, and he's saying, well, there's just the hint of the possibility of maybe some evidence that there might have once been life on Mars. And then it shows the press, all the reporters, jumping up and down, screaming, "Life on Mars!" And then the words at the bottom of the cartoon say, "Is there intelligent life on Earth?"
I just expected scientific controversy, and I didn't quite expect all the public, sort of...
All the media attention.
Well, no, it's not the media attention, it's the larger issues, how it fits into religion, and how it changes our outlook on the world and that kind of thing.
The scientists suddenly found themselves being questioned on matters well outside their area of expertise, like the day they appeared before the House Subcommittee on Space and Aeronautics.
These figures that we use, a 4.5 billion year old rock on Mars, a huge impact about 16 million years ago, and we have a lot of people that are pretty satisfied with the Bible's reflection of the creation and of time, and I have a hard time pulling those together. Does anybody want to touch that?
The gentleman from NASA might not have wanted to touch that, but there were people all over the world considering the implications.
It was a few days before I was about to leave Castel Gandolfo, our observatory in Italy, to come back to the U.S.
Guy Consolmagno is a planetary scientist as well as a Jesuit brother assigned to the Vatican Observatory. He and Dan Britt feel a proprietary interest in the Mars rock. Britt because he's a project manager for an experiment on an upcoming Mars flight. Brother Consolmagno because he published an early paper showing how chemistry could determine where rocks came from.
I couldn't sleep. So I got up at 4 in the morning and turned on television because I knew there was an Italian TV station that carries CBS News at 4 in the morning. I turned it on, and the opening story was Dan Rather talking about a rock that showed life on Mars.
Oh, I saw that too.
And my
he
jaw
was
dropped.
excited.
He was
really
excited.
excited. He was more excited than almost anybody I saw that day.
As for reconciling the religious and the scientific,
these are the two thickest books in my library. One is the Bible, one is Misner Thorne and Wheeler's gravitation textbook. And it's about general relativity, it's about the shape and the warp of the universe. Besides the fact that they're the two thickest books I've got, and they both, I believe, have enormously fascinating truths in them, they're fundamentally different in what they're talking about and how they go about it. And one example of that is simply, the Bible was written 2,000 to 3,000 years ago, and it's still relevant. Gravitation was written 20 years ago, and it's already out of date.
A lot of things have come together in the last 20 years. Remember, it's only been 20 years that we've been collecting Antarctic meteorites, and someone thought to go and look.
This rock, if this idea of life holds up, this is going to matter. This will be something that's remembered like a Rosetta Stone, like the key bit of evidence in favor of plate tectonics, like the key bit of evidence going back to Darwin, or possibly bigger than any of those. We've always talked about life on other planets. And philosophers have always argued back and forth, going back thousands of years, about the possibility of other worlds and creatures living on other worlds. But this is the first time that we actually, we hope, have the hard evidence. And firsts are always fun.
I like it all sort of listening and
The guy custom, I always butcher his last name. I mean, he's been on the Colbert Report at least a couple of times talking about astrobiology in general, life on other planets, and it's fairly reasonable. I mean, maybe it didn't come across really reasonable in this clip here, but I just wanted to play the clip to give you a little bit of a flavor of some of the reaction that occurred. Well, at this point, it's a little bit more than 15 years ago. There was the media buzz. There were the editorial cartoons. There were the people complaining about trying to fit 4-billion-year-old meteorites into a particular narrative of the origin of the universe that doesn't allow for such great dates. What's your reaction to the reaction, I guess? Let me just put it that way.
It was kind of funny.
Kind of funny.
To whose reaction though? Like scientists or media or everybody else?
Let's talk about the media reaction.
Ridiculous. I mean, that's kind of exactly how it happens, regardless of the year. Yeah.
So, you know, I think if we get better data about life on Mars, do you think we'll have the same kind of media reaction?
Right. I think so.
Think so?
I think the media reacts that way with just about everything. They like take everything and like spin it out of proportion and warp the truth.
No lie.
I think it'll be more negative because just how people view government now. It's just gonna be like, oh no, something bad's gonna happen. They knew this the whole time or something.
Yes, NASA's either been sitting on the evidence, or NASA's making up the evidence, or...
But if we even find more evidence of life, it'll probably not be given to attention more because we don't have like, it'll probably be like a little microscope or like a channel system like that.
It'll trend on Reddit for a little bit and then go away.
But here they have like a photo of what looks like a bacteria, and that was probably eaten up more by the media than anything else.
Yeah. So, any other reactions? I mean, do you see... I mean, if we had conclusive evidence that there were actually fossilized life on... Let me just back up a little bit. This work triggered hundreds, at least, maybe thousands of follow-on studies by other researchers. There's been a lot of work looking at the magnetite crystals, you know, how they compare to those found in terrestrial bacteria. Are they really, you know, more regular than you would expect from non-biological processes? Were the carbonates formed at low temperatures, or were they formed at temperatures too high for life? So there's been a lot of work that has followed up on this. A lot of controversy about the size of those bacterial structures, which in turn triggered a re-examination of life on Earth. And there's a lot more interest in actually looking for and studying what are called now nanobacteria. You know, it may be that we never found nanobacteria on the Earth before because we never looked for them. Okay, so we changed this mindset. So it's been a very productive paper in terms of triggering a lot of subsequent follow-up work. If I were to characterize this paper now, the general consensus is it would be, well, they had some interesting evidence, but at this point it's not a convincing case. Carl Sagan a long time ago made the point, you know, if you're going to make an extraordinary claim, you actually have to have extraordinary evidence to back that up. And while, you know, these 4 lines of evidence that they presented would be consistent with a biological origin, in the case for most researchers, that's not a tight enough case to rule out non-biological causes. But, you know, at this point, do you think society has so much factored in the idea that, of course, there's life elsewhere, that it would not be jarring if we actually did find life on Mars? you think still people would freak out?
The fact that there's still movies about aliens being made and people still watch them like very intently, I think that if we found like further evidence of life on Mars, it would be crazy.
Okay. How many of you think we will find evidence for past life on Mars?
Like ever, or?
At some point in the past. Well, within this century.
We probably will, as technology advances.
So, I mean, how many of you think basically, given what you know about Mars, that it was likely that at some point, at least in the past, Mars had living organisms? How many of you think that life might be hanging on in nooks and crannies? Yeah, we won't take the time to talk about, I mean, what people are most interested in right now with life on Mars is looking at evidence that there's active production of methane on Mars periodically, which again could be non-biological, but on Earth, like 90% of the methane that's produced on Earth is produced by living organisms. So